So we have our two-slit problem here again, and this is showing us that if we go straight down the middle here, so right to this central bright fringe, what happens is the path length difference is 0, so we have constructive interference. Our light from the two slits are perfectly in sync. If we move to an angle where we have our first dark fringe here, this means that the path length difference is equal to 1/2 of the weight times the wavelength, lambda, so this is kind of upside down y. So that means m is equal to 1, this becomes 1/2, and so 1/2 lambda is equal to the distance d between the two slits times the sine of theta, which is this angle here. So if we keep moving, now we go to a bright spot where the path length difference is now equal to exactly the wavelength. So we have a so-called bright fringe, and then it keeps going. We go to a dark fringe where the path length difference is 1.5 times the wavelength, and then bright again when we get 2 times the wavelength. So the idea is that this oscillation continues, and so if you see an interference pattern where you have a whole bunch of bright and dark spots, then it's likely to be interference due to multiple slits. So one common use of this is to make a diffraction grating. So diffraction grating is where you have a large number of slits, so they're all evenly spaced, and that means that it produces this nice pattern like this. This is going to produce a very distinct bright spots, and this is especially useful if you want to accurately measure the wavelength of light. You can use this as a measure to, you measure the angle very precisely, and if you can do that, then you know the wavelength to a high degree of certainty. So this is going to produce a pattern, and the angle between the bright spots will be lambda divided by the distance between the holes in the grating. Okay, so let's do our example here. So here we're going to do a two-slit experiment where the distance between the slits is 8.5 times 10 to the minus 5 meters, and the screen is 2.3 meters away. If the 10th bright fringe is 12 centimeters from the central fringe, we want to know the wavelength of light that is used in the experiment. Okay, so we have our formula here for the constructive interference. So m lambda is equal to d sine theta. We know m, so that's 10. It's the 10th fringe, so m is equal to 10. We know d, so that's our 8.5 times 10 to the minus 5 meters. But we do want to figure out what our angle theta here is. Well, we can do some trigonometry. So we've drawn our right triangle here, where the hypotenuse is the path length, the distance to the screen is the adjacent side, and the distance from the center to the fringe is the opposite. So that means that the tangent of theta is equal to the distance to the fringe divided by the distance to the screen. So the inverse tangent of the distance between distance to the fringe divided by the distance to the screen is equal to theta. So that means the inverse tangent of 0.12, right, we converted centimeters into meters, divide by the distance to the screen, and take the inverse tangent. And if we do this, that gives us that the angle is 2.99 degrees. Now we have the angle, 2.99 degrees, so we can write down our formula. So d sine theta is equal to m lambda. So if we want to solve for lambda, we'll just divide by m. So we get d sine theta divided by m is equal to lambda. So yeah, we can pretty much plug and chug now. So this is 8.5 times 10 to the minus 5 meters times the sine of 2.99 degrees divided by 10, which is our integer. So this is the 10th fringe. And that means the lambda here is equal to 443 nanometers. So that's sort of some bluish light. So that seems like a reasonable value for a beam of light. Okay, and so that's how you do it. You measure the distance. You can figure out the wavelength of light to a pretty high degree of accuracy. All right, so it's your turn. So you'll have a problem a lot like this one to do. I think we'll stop here for this week, so we'll finish up our unit on interference on Tuesday. I think we'll mostly be looking at thin film interference there. Then we're going to start thermo on Thursday. So, all right, good luck and take care of yourself.